5 students, Dr. John Schrage. Hey, that quote that you just saw was by Wallace Brecker. I don't know exactly if that's how to pronounce his name, Brecker or something like that. Anyway, he is the scientist who back in the 1970s coined the term global warming. I think that's kind of an interesting little bit of trivia about that guy. Today we are going to be talking about the greenhouse effect and greenhouse gases and so on. Obviously in a class called, the science of climate change, we've actually kind of already talked about this a little bit, and we're going to see more about it in more detail later. But this is kind of a central understanding of what the greenhouse effect is doing and how it does it. And it's going to be working by making changes to the Earth's energy balance that we learned about in the last lecture. I mean, we know from observations that the planet is getting warmer. I mean, these numbers that are on this diagram from NASA are observations that come from satellites and radiometers at the surface of the Earth and so on. These are facts. These are nothing to be argued with. And we know from a very careful examination of the energy balance of the Earth that these processes that are illustrated on this diagram here, these arrows up and down and so on, are the processes that are controlling the radiation in our climate system. And by changing any of these processes, we would have consequences for the temperature of the surface of the Earth. Before we delve into the whole greenhouse effect, we could think of a simpler example of a way that we could change the radiation balance of the Earth. For example, look down there in that red box that I have there. That is radiation that is being absorbed by the surface of the Earth. That is shortwave radiation from the sun that is making it through the Earth's atmosphere and actually being absorbed by the surface of the Earth. It comes to a number of 163.3 watts per square meter when averaged over the whole planet. Okay, what actually determined that number? What factors made that be the answer? Well, it turns out there were 4 factors that were determining the amount of radiation that was absorbed of shortwave radiation that was being absorbed by the surface of the Earth. One was how much radiation actually makes it from the sun through 95 million miles of space to the top of the Earth's atmosphere. 2, the reflection off clouds and gases in the atmosphere and aerosols and things like that. 3, absorption by things like clouds and gases and aerosols and so on in the atmosphere. And 4, how much radiation is actually reflected off the surface of the Earth, how much is reflected by the ground. We could mess with any of these processes and make changes to the Earth's energy balance, but just for the sake of argument, let's just choose that 4th one, the reflection of radiation off the surface of the Earth. Now, this is reflection of shortwave radiation off the surface of the Earth. That is what albedo is all about. Remember how much reflection there is of shortwave radiation off of a surface? Alright, well, based on these numbers here, if you actually do the math, you end up with an albedo of the surface of the Earth is about 0.123, or 12.3% overall. For the surface of the Earth, that doesn't include things like clouds and stuff like that. For the surface of the Earth, the albedo is about 12%. Well, what if we change that number? If the albedo of the surface of the Earth would go down, if the surface were to become darker, we would absorb more of the shortwave radiation that made it through the Earth's atmosphere. That number over there on the left, 163.3 watts per square meter, would go up. We would have an increase in the amount of energy into the surface of the Earth. Temperature would go up. And if the albedo went down, let's see here. And similarly, if we did the other way around, if we made the albedo of the surface of the Earth go up, we would be reflecting more shortwave radiation, and the amount of energy into the surface of the Earth, in the form of shortwave radiation being absorbed, would go down, and the temperature of the Earth would go down. There are other ways, though, that we could mess with these processes that are in the Earth's energy balance that would result in a change in the temperature of the Earth. For example, as happens in the greenhouse effect, we could mess with the absorption and emission of long-wave radiation by clouds and greenhouse gases in the Earth's atmosphere. Clouds and greenhouse gases are selective absorbers. They don't absorb the shortwave in general. In general, they don't absorb very much shortwave radiation as they pass through the Earth's atmosphere. They generally transmit it. But they do absorb a lot of the long-wave radiation that is emitted by the surface of the Earth. They also emit long-wave radiation. Those gases in the atmosphere emit long-wave radiation upward towards space and downward towards the surface of the Earth, where it gets absorbed and increases the temperature of the surface of the Earth. A fair question to ask is, how would the energy balance of the Earth be different if the greenhouse gases didn't do that? By the way, notice that abbreviation GHG, greenhouse gases. we can mess with this diagram here that we got from NASA and figure out how would the Earth be different if the greenhouse gases didn't do that. Alright, because remember, from way back in like the first module of the course or whatever, the greenhouse effect is a perfectly natural thing. It's part of how the planet works. We might be enhancing the greenhouse effect by burning fossil fuels and so on, but let's figure out what the natural effect of this is first. Okay, so this is actually, in this black box here, this is actually a slide from the previous lecture that I've just kind of put up here. And in that slide, we figured out the energy balance for the surface of the Earth. There were these different terms that were energy in, and then in parentheses, those were terms that were energy out from the surface of the Earth, and there was that small residual of 0.6 watts per square meter that was how much the surface of the Earth is actually warming. We had energy in, and we had energy out with respect to the surface of the Earth. Now, the energy in terms, the 163.3, that is shortwave radiation that makes it through the Earth's atmosphere and gets absorbed by the surface of the Earth. If we're going to be doing a little thought experiment here about getting rid of the greenhouse gases or not having the greenhouse gases affect long-wave radiation, we're not going to change that number. On the other hand, that other number, 340.3, that is long-wave radiation that's being emitted downward by greenhouse gases. Well, if we're saying the greenhouse gases don't do that anymore, we're going to take that term and we're going to put it to 0. But right in the real world, it's 340 watts per square meter. Now, over there on the right-hand side of the equation, well, in the parentheses anyway, over there, two of those numbers we're not going to change. One, if you remember, was about conduction of heat from the surface of the Earth into the atmosphere. Most of the time, the ground is warmer than the atmosphere. We won't change that number. It's 18.4. Let's just, for a thought experiment, not change that number. And remember that last number, 86.4, that was the number of watts per square meter that are transferred from the surface to the atmosphere by the cooling process of evaporation. Again, let's save that for ATS 113 when you take that class, because I know you're going to be so thrilled you're going to want to take that class. We're not going to change that number for now. What about this 398 number here? This was long-wave radiation that is being emitted by the surface of the Earth. Stephen Boltzmann's law says that the surface of the Earth, being made of matter, should be emitting radiation, and the amount of radiation it is emitting is determined by the temperature of the Earth. So since we're making changes to the energy balance of the Earth, we're going to be changing the Earth's temperature. This number then is going to change as the temperature changes due to the greenhouse gases being taken out of the atmosphere in order to keep the same energy balance. So if I take that same equation that was up there last lecture, in the blue there, and I say, let's change that energy balance so that there is no greenhouse effect. All right, we took out that number from energy in and changed it to 0, where it is the energy that is coming down from the atmosphere, where clouds and greenhouse gases are emitting long-wave radiation downward. That became 0. And to make the whole math work out, that energy that is emitted by the surface of the Earth, long-wave radiation radiated upward in the Earth's atmosphere, has to change to 57.9. That's what we solved for. That would be how much radiation every square meter is emitting every second. It's the watts per square meter. 57.9 is our new answer. It used to be almost 400. Now it would have to, without greenhouse gases, it would have to be 57.9. The new rate at which the surface would be emitting radiation would have to be 57.9 watts per square meter if the greenhouse gas didn't work. I'm sorry, if the greenhouse effect didn't work. Well, if you plug, that's the amount of radiation being emitted according to Stephen Boltzmann's law. Plug that in and solve for the temperature that it takes the surface of the Earth to be so that it emits 57.9 watts per square meter, and you get a whopping 178.8 Kelvin. I did the math. That works out to negative 94 Celsius, or 138 degrees Fahrenheit below 0. Wow, 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 wow. The real temperature of the Earth is about 288 Kelvin, which is, I don't know, about 57 Fahrenheit is the average temperature of the Earth. Wow, our planet would be a whole lot colder if it weren't for the natural greenhouse effect. If we didn't have that heat that was coming down from the clouds and greenhouse gases in the Earth's atmosphere, the result is to maintain energy balance, we end up with a much colder planet. Yes, because the Earth really is actually too far from the sun to have things like life and liquid water and things like that. It's only because we have a greenhouse effect that we aren't living on a frozen dead rock. Okay? You know, in the same way, Okay, if our planet would be much colder if the greenhouse gas effect wasn't working, it would be much warmer if the greenhouse effect was working better. The classic example of that would be Venus. Okay, I'm not going to work through the energy budget of Venus. Venus is hot because it's closer to the sun than we are, but it isn't that much closer to the sun than we are. The main reason why Venus is hot enough to melt lead is because has such a runaway greenhouse effect. The atmosphere of Venus has so much greenhouse gases, when you actually work out the math, the surface temperature of Venus is in the vicinity of 1,000 degrees Fahrenheit. It's much too hot to support daily life, despite the fact it isn't that close to the sun. Therefore, without all those clouds and greenhouse gases emitting long-wave radiation down towards the surface of the Earth would simply just be that much colder. The greenhouse effect is a key aspect of how our planet works. Now, to explain how that all works and what is the greenhouse effect actually doing, we'll go on to the second part of this lecture. But first, I want to ask 2 or 3 quick questions here. Real quick, question 1. All else being equal, if the albedo of the Earth were higher, the temperature of the surface of the Earth would be A, lower, or B, higher. Pretty straightforward. Take one of those 2 choices, follow the link, and get some feedback before we move on to question 2.